Let us consider some examples from the course pack. The first molecule is methane, which has slightly polar bonds and a tetrahedral molecular geometry. If we refer to our mnemonic, funny old clown, we can see that carbon is more electronegative than hydrogen. This would make the hydrogen atoms delta positive and the carbon atoms delta negative. The bond dipoles would be oriented in this fashion. Initially, it may not be 100% obvious that the bond dipoles cancel based on the drawing before us. A three-dimensional representation of this molecule helps us see that a tetrahedral is like two bent structures joined at the middle carbon atom, and that the bond dipoles from each bent structure would indeed cancel. Further, the fact that this tetrahedral structure is completely symmetrical is another indication that the bond dipoles will cancel. Lastly, except for some considerations like infrared spectroscopy, organic chemists normally consider the carbon-to-hydrogen bond to be essentially nonpolar. This is because the difference in electronegativity between the carbon and the hydrogen atom is small. In the Pauling scale, carbon is about 2.5 and hydrogen is about 2.1. Therefore, rarely would we do this more complete analysis for methane or other hydrocarbons. All of this is consistent with methane having a zero dipole moment in Debye units. If we consider, however, chloromethane molecule, which is represented as the next structure to the right in the course pack, we know that the carbon-chlorine bond is indeed polar. Because chlorine atom is more electronegative than the carbon atom, consider again our mnemonic funny old clown, we would say that the chlorine atom is delta negative and that the carbon atom is delta positive. I draw a bond dipole in the direction of the chlorine. I consider that the hydrogen to carbon bonds are essentially nonpolar, and therefore this entire molecule will have a molecular dipole in the direction of the chlorine atom. As indicated, if you put this molecule between charged plates, a dipole moment of 1.94 Debye will be measured. In a similar way, we can consider the bromomethane molecule. It has a bond dipole in the direction of the bromine atom, and we can also draw a molecular dipole considering the three-dimensionality or the molecular geometry of this molecule. It has a dipole moment of 1.79 Debye. You may have noticed that the bond dipole and the molecular dipole arrows were drawn shorter for the bromomethane as compared to the bond dipole and molecular dipole arrows for the chloromethane. Recall that these arrows are vector quantities. A longer arrow reflects a greater polarity, a shorter arrow a smaller polarity. Therefore, the shorter arrows for bromomethane indicate a smaller polarity as compared to chloromethane. We would predict that the bromomethane molecule to have a smaller polarity because there's a smaller difference in electronegativity between the carbon and bromine atoms as compared to the carbon and chlorine atoms. Consider again our funny old clown mnemonic. We see that bromine is closer to carbon as compared to the chlorine, which represents a smaller difference in electronegativity.